Hello everyone, I'm Shuayang from PKU and today I'm going to introduce our paper, FRESCO, Spatial-Temporal Correspondence for Zero-Shot Video Translation. Here is an overview of what FRESCO can do. FRESCO can render a source input video into a temporal coherent video with the style specified by prompts. Our method builds upon Stable Diffusion and introduces a novel FRESCO constraints for temporal consistency. FRESCO, Frame Spatial Temporal Correspondence, is to improve the spatial and temporal consistency between the output video and the input video. For implementation, we propose to optimize the network feature and modify the self-attention layers to incorporate our FRESCO constraint. We can see that the temporal constraint and the spatial constraint can effectively improve the inter-frame and intra-frame consistency after editing, and the joint constraints give the best result. Stable Diffusion has achieved remarkable success in image generation and editing. Naturally, we are curious about the potential of its application in video domains. Researchers have proposed three solutions. The first solution is to train a large video model on large-scale dataset, which requires significant computing resources. The second solution is to fine-tune Stable Diffusion on a single video, which is less efficient. The third solution is zero-shot methods, which add temporal constraints to the diffusion inference process for temporal consistency. Zero-shot methods require no training, therefore are compatible with existing image models, showing promising potential. In our previous work, we rendered a video. We introduced temporal constraints based on object flow. Based on the object flow estimated in the input frames, we warp the translated previous frame to the current frame as pixel-level guidance. However, object flow is not always available or accurate. For example, changes in object flow during manipulation may result in inconsistent guidance, leading to issues such as parts of the foreground appearing in stationary background areas without proper foreground movement. In areas where occlusion or rapid motion hinders object flow estimation, the resulting constraints are insufficient, leading to distortions. In this work, we seek another spatial constraint as a complementary to the temporal constraint. We focus on preserving intra-frame spatial correspondence. That's to say, we would like semantically similar content to be manipulated cohesively, maintaining its similarity post-translation. For example, the two white point stars will be similar since they are similar in the input. The same goes for the white triangles. In this way, the output will be more consistent with the input, which will also improve the temporal coherence since the input video is temporal coherent. Specifically, we follow the SD-edit and the control net as the image-to-image translation pipeline and adapt the pipeline to video translation in two ways. First, in each layer of the unit decoder, we propose to directly optimize the feature to improve temporal and the spatial consistency with two loss functions. The temporal consistency loss enforces consistency between aligned features of consecutive frames. And the spatial consistency loss enforces the consistency of the gram matrix of the features between the translated frame and the input frame. Note that gram matrix is the correlation between every two elements of a vector, which can effectively measure the spatial relationship within a single frame. Then we modify the self-attention layers, giving a novel FRESCO-guided attention. It contains three attention layers. We extend the self-attention to spatial-guided attention. Its attention weights are based on the input frame rather than the edited frame. For example, for this X toucan in the foreground, the attention weights are high in the foreground region and are low in the background region. Then we modify the cross-frame attention. There are two kinds of cross-frame attention. One uses all available frames as reference, which is computationally inefficient. Another uses the first frame or the previous frame as a reference, which cannot handle the newly emergent objects. We propose efficient cross-frame attention by eliminating redundant toucans and only attend to unique toucans across different frames. Finally, we use temporal guided attention, forcing every token to only attend to the corresponding token along an optical flow in other frames. Our attention adaptation indirectly improves coherence by imposing soft constraints on how and where to attend to valid features. Meanwhile, our feature adaptation directly optimizes the feature towards high spatial and temporal coherence with the input. We find that combining these two forms of adaptation achieves the best performance. Let's see some experimental results. We compare with 4-0 methods. Control video fails to generate a plausible appearance of the fox. Text to video 0 and re-render a video struggle to maintain the cut pose. Token flow sometimes fail to translate the appearance. Our method can generate consistent video based on the proposed FRESCO guidance. We study the FRESCO constraints in detail. The baseline model solely used cross-frame attention for temporal consistency. By introducing the temporal-related adaptation, we observe improvements in consistency, such as the alignment of textures and the stabilization of the song's position across two frames. Meanwhile, the spatial-related adaptation aids in preserving the pose during translation. Combining these two kinds of constraints achieve the best performance. Here, we study two forms of adaptation in detail. Clearly, each enhancement individually improves temporal consistency to a certain extent, but neither achieves perfection. Only the combination of the two completely eliminates the inconsistency observed in hair strains. For our efficient cross-frame attention, attending to only the previous frame fails to synthesize the newly appearing fingers. The efficient cross-frame attention achieves the same performance as full-frame reference, but reduces the region that needs to be attended to by more than 40% in this example. By increasing the weight of temporal consistency loss, we can effectively enhance consistency between two transformed frames in the background region. By increasing the weight of spatial consistency loss, we can boost the pose consistency between the transformed cut and the original cut. Here are more results. In conclusion, in FRESCO, we introduce both temporal and spatial consistency constraints to Stable Diffusion, effectively extending it to the video-to-video translation tasks. That's all of my talks. Thank you. FRESCO is open sourced. For more information, please visit my GitHub page.